imagine this. You are standing at the edge of the largest structure humanity has ever built. It stretches out before you, a cylinder so vast that clouds form inside it. Trees grow along its inner walls. Rivers flow in gentle curves that defy everything you know about gravity. 10,000 people call this place home. It has schools, hospitals, farms, parks, and laboratories. It has everything a small civilization needs to survive. And in a few hours, this entire world, this city wrapped inside a metal shell, will leave Earth forever. It will point itself toward a star so far away that the light you see from it tonight left that star 4 years ago. The people who board this ship today will never see that star up close. Their children will never see it either, nor their grandchildren. If everything goes according to plan, it will be the great-great-great-great-grandchildren of today's passengers who will finally arrive. 200 years from now, 8 generations from now, that is the promise of a generation ship. But here is what nobody talks about. Here is what the science fiction movies never show you. Here is what the dreamers and the visionaries quietly ignore when they paint their beautiful pictures of humanity sailing among the stars. The math does not work. The biology does not work. The psychology does not work. The ecology does not work. The sociology does not work. And the engineering most certainly does not work. Not over the timescales we are talking about. Not with anything we know. Not with anything we can reasonably predict knowing in the next century. A generation ship would not deliver humanity to the stars. It would become a tomb. A sarcophagus hurtling through the emptiness between solar systems at unimaginable speed, carrying the frozen remains of a dream that died somewhere around generation 3 or 4. A flying graveyard. And today, I am going to show you exactly why. Not with speculation. Not with opinion. Not with dramatic storytelling for its own sake. With science. With research. With data. With the cold hard mathematics of physics, biology, genetics, and human psychology. We are going to walk through every single way a generation ship fails. Every angle, every system, every weakness. From the metal in its hull to the DNA in the cells of its passengers. From the air they breathe to the society they build. From the radiation that bathes them to the evolutionary forces that reshape them into something that is no longer quite human. This is going to be one of the most detailed explorations of this topic you have ever encountered. We are going deep. We are going to places that most people never think about when they imagine interstellar travel. And by the end, you will understand something profound about the human condition itself. About what it means to be a biological creature evolved for a very specific world, trying to survive in an environment that is fundamentally hostile to everything we are. Before we begin this journey, if you find this kind of deep scientific exploration valuable, if you want more content that takes big ideas and examines them from every possible angle with honesty and rigor, then take a moment right now to hit that subscribe button. Ring the notification bell. Leave a like on this video. And most importantly, drop a comment below telling me whether you would board a generation ship if given the chance. I am genuinely curious, because by the end of this video, I suspect your answer might be very different from what it is right now. These videos take enormous amounts of research and effort to produce, and your engagement is what makes them possible. So thank you. Now let us begin. I want to start with a story. A true story. A story about 8 people who tried to do something that sounds simple but turned out to be almost impossible. They tried to live inside a closed world. And they did it right here on Earth, with every advantage you could possibly imagine. The year was 1991. The place was Oracle, Arizona in the United States. A team of scientists and engineers had spent nearly a decade and $200 million building something extraordinary. They called it Biosphere 2. The name tells you everything about its ambition. Biosphere 1 is Earth itself. The entire planetary ecosystem. Every ocean, every forest, every desert, every coral reef, every microorganism, every atmospheric cycle, every geological process. All of it working together in a system so complex that we still do not fully understand it. Biosphere 2 was supposed to be a miniature version, a closed ecological system covering 3.14 acres, sealed under glass and steel. Inside, they had created multiple biomes: a rainforest, a coral reef ocean, a mangrove wetland, a savanna grassland, a fog desert, and an agricultural area designed to feed the crew. They stocked it with nearly 4,000 species of plants, animals, and microorganisms, all carefully selected to create interlocking food webs and nutrient cycles. On September 26, 1991, 8 people walked inside and the doors were sealed behind them. The plan was to live inside for 2 full years, completely self-sufficient, no food coming in, no waste going out, no air exchange with the outside, just like a spaceship. This was, in many ways, a direct test of the technology and concepts that would be needed for a generation ship or a Mars colony. What happened next is one of the most important cautionary tales in the history of space science, and almost nobody knows the full story. Within the first few months, things began to go wrong, not dramatically, not catastrophically, insidiously, slowly, in ways that were difficult to diagnose and almost impossible to fix. The first problem was oxygen. The oxygen level inside Biosphere 2 began to drop, slowly at first, then faster. The plants were supposed to produce enough oxygen through photosynthesis to sustain the 8 crew members. They did not. The oxygen concentration started at 20.9%, which is normal atmospheric level. Within 16 months, it had dropped to 14.5%. That is equivalent to the oxygen level you would experience at an altitude of about 4,000 meters. Imagine living at the top of a very high mountain, constantly, with no way to come down. The crew experienced chronic fatigue, cognitive impairment, difficulty sleeping, and could barely complete physical tasks. For months, scientists could not figure out where the oxygen was going. Plants produce oxygen and consume carbon dioxide. That should balance. Eventually, they discovered something unexpected. The concrete used in the construction of the structure was absorbing oxygen through a chemical carbonation process. The very building materials of their sealed world were slowly suffocating them. This is the kind of problem you cannot predict. The kind of hidden interaction between systems that only reveals itself over time. But it got worse. The carbon dioxide levels fluctuated wildly, following seasonal cycles that were far more extreme than anyone had modeled. The agricultural systems produced only about 80% of the food the crew needed. They were chronically hungry for 2 years, not starving, but never fully satisfied, always operating at a caloric deficit. This affected their energy, their mood, their cognitive function, and their interpersonal relationships. The ecological systems began to collapse in ways nobody had predicted. 25 vertebrate species that had been introduced went extinct inside the enclosure. Every single one. Most of the pollinating insects died. Without pollinators, many plant species could not reproduce. The populations that thrived were the ones nobody wanted. Cockroaches exploded in number. Crazy ants, a particularly aggressive invasive species, took over vast areas of the enclosure. Vines and morning glory plants grew out of control, smothering other vegetation. The carefully designed biomes began to blur and degrade. The coral reef ocean suffered from excess carbon dioxide dissolving into the water, making it acidic. Sound familiar? It is exactly what is happening to Earth's oceans, but on a compressed timescale. And then there were the humans. The 8 crew members, carefully selected for psychological stability and teamwork, fractured into 2 hostile factions of 4. They stopped speaking to each other, except when absolutely necessary for operations. 2 years of confinement, hunger, low oxygen, and the stress of watching their world slowly fail around them had broken their social bonds completely. The experiment was declared a failure. External oxygen had to be pumped in to keep the crew alive. The second mission, beginning in 1994, lasted only 6 months before being terminated due to management disputes and further ecological collapse. Now here is what I want you to understand. This experiment had every possible advantage. It was on Earth. If something went truly wrong, they could open the doors and walk outside. They had access to external scientific expertise. They could communicate freely with the outside world. They had $200 million of the best engineering available at the time. The experiment lasted only 2 years. And it still failed. A generation ship asks you to do the same thing, in a much smaller space, with much less margin for error, surrounded by the vacuum of space rather than the Arizona desert, with no doors to open, no external help, no rescue. For not 2 years, but 200 years. If we could not maintain a closed ecosystem on Earth for 24 months with unlimited backup options, what makes anyone think we can do it for 2 centuries with 0 backup options? This is where our journey begins, and from here, it only gets darker. Let us start with the most basic question. What is a generation ship exactly, and why do we even need one? The answer to the second question is distance. The universe is unreasonably, almost maliciously, large. The nearest star system to our own is Alpha Centauri, a triple star system located 4.24 light-years away. A light-year is the distance light travels in 1 year, and light moves at 300,000 kilometers per second. So 4.24 light-years is approximately 40 trillion kilometers. That number is so large, it becomes meaningless. Let me put it differently. The fastest object humanity has ever launched is the Parker Solar Probe, which reached speeds of about 630,000 kilometers per hour. At that speed, which is far beyond anything we could sustain for an interstellar journey, it would take the Parker Solar Probe about 7,000 years to reach Alpha Centauri. 7,000 years. All of recorded human civilization, from the first Sumerian clay tablets to this video you are watching right now, fits inside about 5,000 years. We are talking about a journey longer than all of human history. Even with optimistic future propulsion technologies, nuclear fusion drives or nuclear pulse propulsion, we might achieve speeds of 5 to 10% the speed of light. At 10% light speed, the trip to Alpha Centauri takes about 42 years. That is within a single human lifetime, though barely. But 10% light speed is extraordinarily optimistic. It requires energy budgets that dwarf anything we have ever conceived of engineering. More realistic assessments put feasible interstellar travel speeds at 1 to 5% light speed, which means journey times of 80 to 400 years. If the journey takes more than 1 human lifetime, you need a generation ship. A vessel large enough and sophisticated enough that people can live their entire lives aboard it. They are born there, they grow up there, they work there, they raise their own children there, they grow old there, they die there, and their children continue the journey, and their children's children, until, generations later, their descendants arrive at the destination that their ancestors chose for them. The concept is old. Robert Goddard, often called the father of modern rocketry, proposed the idea as early as 1918. In 1929, the physicist J.D. Bernal wrote a paper called The World, the Flesh and the Devil, in which he proposed hollow spherical vessels carrying entire populations through interstellar space. Later designs included the O'Neill cylinder, a rotating habitat 32 kilometers long and 6.4 kilometers in diameter, using rotation to simulate gravity on its inner surface. The British Interplanetary Society's Project Daedalus in 1978 proposed a fusion-powered probe. Project Longshot in 1987 explored antimatter-catalyzed fusion. These designs are magnificent. They are inspiring. They represent some of the finest engineering imagination our species has produced. And they all share the same fundamental flaw. They assume that the systems they describe, both mechanical and human, can function reliably for centuries in the most hostile environment imaginable with zero external support. They cannot. And I am going to show you exactly why, starting with the most fundamental law of physics. There is a law in thermodynamics, the second law, that says something terrifyingly simple. In any closed system, disorder increases over time. Entropy, which you can think of as disorganization, as breakdown, as chaos, always grows. Things fall apart. Metal corrodes, seals degrade, bearings wear down, circuits fail, filters clog, pipes develop leaks, welds crack, software accumulates errors. This is not a possibility. It is not a risk. It is a mathematical certainty. The second law of thermodynamics is one of the most fundamental and inescapable laws in all of physics. It has never been observed to be violated. Not once. Not anywhere. Not ever. On Earth, we fight entropy constantly. When your car breaks down, you take it to a mechanic who replaces the worn parts with new ones manufactured in a factory, from raw materials mined from the ground, transported by ships and trucks powered by fuel extracted from deep underground. When a bridge corrodes, engineers bring in new steel made in furnaces fed by coal, transported by rail from mines across the country. Our entire industrial civilization is one vast machine for fighting entropy, and it requires the resources of an entire planet to do it. A generation ship has none of this. It is a closed system. Everything it will ever have, it must carry with it from the beginning. Every spare part, every raw material, every tool, every chemical, every replacement filter and seal and bearing and circuit. For 200 years of continuous operation. Think about what that means. Consider just one example. The life support system that scrubs carbon dioxide from the air and provides oxygen. This system must operate continuously, without interruption, for 200 years. It contains filters, membranes, chemical reactants, pumps, fans, sensors, control circuits, and power connections. Each of these components has a finite lifespan. Even the best industrial equipment on Earth is designed for maybe 20 to 30 years of operation before major overhaul. Most components last far less than that. You need spare parts, lots of them. But how many? If a critical pump has a mean time between failures of 50,000 hours, and you need it to run for 200 years, that is 1.75 million hours. You need at least 35 spare pumps for just that one component. But that pump has its own components, seals and impellers and bearings, each with their own failure rates. And the spare parts themselves degrade in storage. Rubber seals harden. Lubricants evaporate. Electronic components suffer from electromigration even when not in use. You could carry manufacturing equipment to make new parts, but manufacturing requires raw materials and energy, and tools that themselves wear out. and skilled operators who must be trained across generations. And the raw materials are finite. You start with a fixed amount of iron, copper, silicon, rare earth elements, polymers, and chemicals. Every time you manufacture something, you consume some of that finite supply. There is no mine to dig, no forest to harvest, no oil well to tap. What you bring is all you will ever have. Now let me give you some real data about what happens to materials in space over time. Between 1984 and 1990, NASA flew an experiment called the Long Duration Exposure Facility. It was a school bus-sized satellite placed in low Earth orbit and left there for 5 years and 8 months. When they retrieved it, they found extensive degradation across virtually every material tested. 34,000 micrometeorite impacts were documented on its surface. Polymers had been destroyed by ultraviolet radiation and atomic oxygen erosion. Metal surfaces showed pitting and corrosion. Thermal blankets had degraded significantly. Optical surfaces were clouded. Seal materials had hardened and cracked. This was in low Earth orbit, still partially protected by Earth's magnetic field, still within the thin upper atmosphere. For less than 6 years, a generation ship would spend 2 centuries in deep interstellar space, far from any protective magnetic field, subjected to far more extreme thermal cycling, and traveling at speeds where even tiny dust particles impact with devastating energy. The thermal cycling problem alone is extraordinary. In space, an object in direct starlight can reach temperatures above 120 degrees Celsius. In shadow, temperatures drop to -270 degrees Celsius. As a generation ship rotates to produce artificial gravity, different sections cycle between these extremes. Every cycle causes materials to expand and contract. Over time, this creates microfractures. The fractures grow. Eventually, they become structural failures. In 200 years of continuous operation, a rotating generation ship would experience millions of thermal cycles. No material known to engineering science can survive this without eventual failure. And then, there are the micrometeorites. Space is not empty. The interstellar medium contains dust particles, ice crystals, and small rocky debris. At the speeds a generation ship would travel, even tiny particles become devastating projectiles. At 10% the speed of light, a particle weighing 1 gram impacts with kinetic energy equivalent to about 200 tons of TNT. That is not a minor hull breach. That is a catastrophic explosion. Even at more modest speeds of 1 to 2% light speed, particle impacts deliver enormous energy. The standard engineering solution is a Whipple shield, a multi-layered barrier designed to break up impacting particles before they reach the pressure hull. These work well for current spacecraft in near-Earth space, where particle velocities are relatively modest. But Whipple shields degrade over time. They are designed for a finite number of impacts. Over 2 centuries of travel through interstellar space, encountering countless dust particles, the shielding slowly erodes. It develops weak points. And all you need is one particle to get through to a critical system. Let me put all of this into a mathematical framework that makes the problem clear. Suppose you have 100 critical systems on your generation ship. Each one is engineered to an impressive 99.9% annual reliability. That means each system has only a 1 in 1,000 chance of failing in any given year. Those sound like great odds. Now, calculate the probability that all 100 systems survive for all 200 years. The math is simple. 0.999 raised to the power of 20,000. That is 100 systems times 200 years. The answer is approximately 0.00000002. That is essentially zero. The probability of getting through 200 years without at least one critical failure, even with incredibly optimistic reliability assumptions, is mathematically negligible. And remember, these systems are not independent. They are interconnected. Power generation feeds life support. Life support feeds habitation. Computing controls power distribution. Navigation requires computing. Communication requires power. A failure in one system cascades into others. This is called common cause failure in reliability engineering, and it makes the actual probability of survival even lower than the already negligible number I just calculated. This is not pessimism. This is not negativity. This is the second law of thermodynamics, applied over timescales that engineering was never designed to handle. Everything breaks, everything degrades, everything fails. Given enough time, entropy wins. Always, without exception. And a generation ship gives entropy 200 years to work. But let us say, for the sake of argument, that we solve the engineering problems. Perhaps we develop self-repairing materials. Perhaps we create manufacturing systems so sophisticated they can rebuild any component from raw atomic feedstock. Perhaps we invent metamaterials that resist thermal cycling and radiation damage for millennia. Let us grant all of that and move on. Because even if the ship survives, the question remains whether the people inside it will. The human body evolved on Earth. Every system in our biology, every cell, every organ, every molecular pathway, was shaped by 4 billion years of evolution in a very specific environment. An environment with exactly 1 g of gravitational acceleration, with a magnetic field that deflects most cosmic radiation, with an atmosphere that blocks ultraviolet light and provides exactly 21% oxygen at sea level pressure, with a day-night cycle of 24 hours, with seasonal variations, with thousands of species of bacteria, fungi, and other microorganisms that our immune system co-evolved with over millions of years. Take a human body out of this environment, and it begins to fail. Not in obvious ways at first, in subtle, progressive, insidious ways that accumulate over time and, crucially, over generations. In 2019, NASA published the results of what is known as the Twin Study. Astronaut Scott Kelly spent 340 consecutive days aboard the International Space Station while his identical twin brother Mark Kelly remained on Earth. Because they share virtually identical DNA, any differences between them after Scott's spaceflight could be attributed to the space environment rather than genetics. The results were profound and deeply concerning for anyone who dreams of long-duration spaceflight. Scott Kelly experienced changes in gene expression that persisted even after returning to Earth. 7% of his genes showed altered expression 6 months after landing. His telomeres, the protective caps on the ends of chromosomes that are associated with aging, initially lengthened in space but then shortened dramatically upon return, suggesting accelerated aging. His cognitive function measurably declined. His carotid artery walls thickened, indicating cardiovascular stress. The shape of his eyeballs changed due to intracranial pressure shifts, a condition now called spaceflight-associated neuroocular syndrome, which affects a significant percentage of astronauts on long missions. His bone density decreased. His muscle mass reduced despite 2 hours of daily exercise, specifically designed to counteract this. 340 days. With 2 hours of daily exercise, with carefully optimized nutrition, with the full support of ground-based medical teams, with the psychological comfort of knowing he would return to Earth, and his body still degraded in measurable, significant ways. Now multiply that by a lifetime. Multiply it by multiple lifetimes. Multiply it by generations. The most obvious physical problem is gravity, or rather, the lack of it. A generation ship would almost certainly use rotation to create artificial gravity. This is the most frequently proposed solution, spinning the habitat so that centrifugal force pushes inhabitants toward the outer wall, simulating the pull of gravity. And for large enough structures, this works reasonably well. But not perfectly. Never perfectly. In a rotating habitat, the Coriolis effect creates subtle but constant forces that distort motion. If you drop an object, it does not fall straight down. It curves slightly. If you walk in the direction of rotation, you feel slightly heavier. If you walk against rotation, you feel slightly lighter. These effects decrease as the radius of rotation increases. For a habitat with a radius of 500 meters, the Coriolis effect is small enough for most activities. But it is not zero. And the human vestibular system, the balance mechanism in your inner ear, is exquisitely sensitive. Some percentage of the population would experience chronic motion sickness. Others would adapt but with altered neurological processing that could have downstream effects we cannot predict. More importantly, in a rotating habitat, gravity varies with radius. At the outer rim, where the floor is, you experience the designed gravity level. But as you move toward the center, gravity decreases. Your head, being closer to the center than your feet, experiences slightly less gravity than your feet. For a habitat radius of 500 meters and a person height of 1.8 meters, this difference is negligible. But for smaller habitats, it becomes significant. And building a habitat with a 500-meter radius means building a structure over a kilometer in diameter. The engineering challenges are immense. But even assuming perfect 1G artificial gravity, which is physically impossible in a rotating system, but let us assume it anyway, there remain serious biological problems with long-term spaceflight. Radiation. It is the silent destroyer. On Earth, we are shielded from most cosmic radiation by two protective systems. First, Earth's magnetosphere. A vast bubble of magnetic field generated by the liquid iron core of our planet deflects the majority of charged particles from the solar wind and from galactic cosmic rays. Second, our atmosphere, equivalent to about 10 meters of water shielding above our heads, absorbs most of what gets through the magnetosphere. Together, these systems reduce our radiation exposure to approximately 0.003 sieverts per year at sea level. In deep interstellar space, you have neither of these protections. The radiation environment is dominated by galactic cosmic rays, which are high-energy particles originating from supernovae and other violent cosmic events throughout the galaxy. These include protons, helium nuclei, and heavier ions like iron, carbon, and oxygen, traveling at significant fractions of the speed of light. They carry enormous energy per particle. And here is what makes galactic cosmic rays so dangerous and so difficult to deal with. They cannot be fully shielded against using any known material. When a high-energy heavy ion strikes a metal shield, it does not simply stop. It shatters into a spray of secondary particles, neutrons, protons, pions, and other debris that can actually increase the total radiation dose on the other side of the shield. This is called spallation, and it means that for galactic cosmic rays, more shielding can actually make things worse. The best shielding materials are hydrogen-rich substances like water or polyethylene, which produce less harmful secondary radiation. But even thick layers of these materials only reduce galactic cosmic ray exposure. They do not eliminate it. Current estimates suggest that even with optimal shielding, crew members on an interstellar vessel would receive between 0.1 and 0.5 sieverts per year. That is 30 to 150 times the exposure on Earth's surface. Now let us consider what this means over generations. A single individual receiving 0.3 sieverts per year for 70 years accumulates a lifetime dose of 21 sieverts. The cancer risk associated with this dose is enormous. But it is not just cancer. Chronic radiation exposure damages the cardiovascular system, accelerates aging, impairs cognitive function by destroying neurons in the hippocampus, weakens the immune system, causes cataracts, and reduces fertility. Research conducted at NASA's Space Radiation Laboratory at Brookhaven National Laboratory has exposed mice to radiation environments simulating deep space. The results are alarming. Mice showed permanent cognitive impairment, including memory loss and reduced ability to learn new tasks. They developed increased anxiety and reduced social behavior. They showed signs of accelerated neurodegeneration similar to Alzheimer's disease. And they showed significant cardiac damage. These were acute exposures designed to simulate a Mars mission of 2 to 3 years. For a generation ship, the exposure is not 2 years. It is a lifetime. Every lifetime. For every generation. The damage does not reset between generations. It accumulates. This brings us to perhaps the most devastating biological threat facing a generation ship. The one that cannot be fixed, cannot be shielded against, and cannot be reversed. The genetic catastrophe. Every time radiation damages a cell in your body, it damages DNA. Most of the time, the cell repairs the damage or dies. But sometimes, the damage is not lethal to the cell, but alters the DNA in a way that gets copied when the cell divides. This is a mutation. If this mutation occurs in a somatic cell, a body cell, it might cause cancer in that individual. But if it occurs in a germ cell, a reproductive cell, it gets passed to the next generation. In a high radiation environment, the mutation rate in germ cells increases dramatically. Most mutations are neutral or harmful. Very few are beneficial. This means that each generation on a generation ship would carry more harmful mutations than the previous one. This is a well-established principle in population genetics called mutational load. On Earth, large populations deal with mutational load through natural selection. Harmful mutations reduce the reproductive success of their carriers, and over time, they are eliminated from the gene pool. But this only works in large populations. In small populations, like those on a generation ship, random chance plays a larger role than natural selection. A harmful mutation might persist and spread through the population simply by luck, because its carrier happened to have many children for reasons unrelated to that gene. This is genetic drift, and in small populations, it overpowers natural selection. When you combine increased mutation rate from radiation with the inability of a small population to purge harmful mutations through selection, you get a phenomenon called Muller's ratchet, named after the Nobel Prize-winning geneticist Hermann Joseph Muller, who described it. The ratchet works in one direction only. Harmful mutations accumulate generation after generation and can never be removed. The genetic health of the population can only decline, never improve. The ratchet only turns one way. The numbers are stark. A study published in 2018 by Cameron Smith at Portland State University calculated the minimum viable population for a multi-generational space voyage. His analysis, using sophisticated population genetics modeling, concluded that a minimum of 10,000 people and possibly as many as 40,000 would be needed to maintain genetic diversity over a 200-year journey. Below this number, genetic drift and inbreeding depression would inevitably destroy the health of the population. A related study by Frederick Marin and Camille Beloufi at the University of Strasbourg in 2013 used Monte Carlo simulations to model population genetics over interstellar travel timescales. Their conclusion was that a minimum of 14,000 individuals would be needed, and even this number assumed careful genetic management of reproduction. Let me explain what inbreeding depression means in practical terms. When a population is small, people inevitably become related to each other over time, even starting with 10,000 unrelated individuals. After several generations of reproduction within this closed group, everyone begins to share common ancestors. The coefficient of inbreeding rises with each generation. This means an increasing probability that an individual inherits two copies of the same harmful recessive gene, one from each parent. On Earth, in a large diverse population, harmful recessive genes are rarely expressed because you almost never get two copies. But in a small, increasingly inbred population, these genes begin to express themselves. The consequences are medically devastating. Increased infant mortality, reduced fertility, weakened immune systems, higher rates of genetic diseases, reduced cognitive function, shorter lifespans, lower birth weights, higher susceptibility to infections. And every generation, it gets worse. The historical evidence for this is clear and abundant. The European royal families, who practiced intermarriage for centuries, suffered from hemophilia, the famous Habsburg jaw, infertility, and many other genetic disorders. And they were not even that isolated, still occasionally introducing genetic diversity through marriages outside the immediate family. A generation ship has no outside genetic diversity to draw upon. Once those doors close and the ship departs, the gene pool is fixed. Whatever genetic diversity you brought is all you will ever have, and it will only decrease over time, never increase. Some have proposed genetic management as a solution, maintaining a database of everyone's genome and using it to determine optimal mating pairs to maximize genetic diversity. In theory, this could slow the genetic decline. In practice, it means telling people who they can and cannot have children with. It means removing one of the most fundamental freedoms in human life, the freedom to choose your own partner. It means creating a society where a computer algorithm decides who sleeps with whom. How long before people refuse? How long before unauthorized pregnancies occur? How long before rebellion against the genetic management system? And when people resist, which they will, what do? Force compliance? And if you cannot enforce genetic management, the population begins its inevitable genetic decline. This is not a technical problem. It is a social problem wrapped around a biological problem, wrapped around a mathematical problem, and none of them have clean solutions. There is one more aspect of the genetics problem that deserves attention. Epigenetics. This is the study of heritable changes in gene expression that do not involve changes to the DNA sequence itself. Environmental factors like stress, nutrition, toxin exposure, and radiation can modify how genes are expressed, attaching or removing chemical groups on DNA or on the histone proteins around which DNA is wound. These modifications can be passed from parent to child. Research has shown that chronic stress causes epigenetic changes associated with anxiety disorders, depression, metabolic syndrome, and immune dysfunction. These changes can persist for multiple generations. The famous Dutch hunger winter study showed that children and even grandchildren of women who experienced famine during pregnancy in 1944 had higher rates of obesity, cardiovascular disease, and mental health problems. On a generation ship, chronic stress is not a risk, it is a certainty. The stress of confinement, of resource limitation, of social conflict, of never seeing open sky, of knowing you will die inside metal walls, of living with the constant low-level awareness that a single system failure could kill everyone you know. This stress would create epigenetic changes that get passed to the next generation, who experience the same stresses plus the inherited epigenetic burden from their parents, creating their own epigenetic changes that they pass on to their children. It is a compounding effect. Each generation slightly more psychologically damaged than the last at the genetic level, before they even experience a single day of life aboard the ship. And now let us talk about that psychological damage directly. Because even if the engineering holds, even if the biology remains functional, even if the genetics stay stable, the mind might not survive. In 2010, an international collaboration led by Russia's Institute of Biomedical Problems began an experiment called Mars 500. 6 volunteer crew members were sealed inside a simulated spacecraft for 520 days, the approximate duration of a round trip to Mars. They could not leave. They had limited communication with the outside world, with artificial time delays simulating the increasing distance from Earth. Their living space was confined, their activities restricted, their social world limited to 5 other people. The results were deeply concerning. 4 of the 6 crew members developed significant sleep disorders, spending increasing amounts of time in bed but sleeping poorly. Depression was documented in multiple crew members. One crew member became so withdrawn and sedentary that he was essentially non-functional for portions of the mission. Cognitive performance declined measurably in some crew members. Social dynamics deteriorated as the mission progressed. And remember the context. These were carefully selected, psychologically screened volunteers who knew the exact end date of their confinement. They knew they could leave in an emergency. They knew it was a simulation. They knew the outside world was right there beyond the walls. And they still broke down psychologically in less than 2 years. A generation ship offers none of these psychological comforts. There is no end date for anyone except the final generation. There is no emergency exit. It is not a simulation. The outside is not breathable atmosphere, but the killing vacuum of space. And the duration is not 520 days, but over 70,000 days. Per generation. Let me take you through what happens to the human mind across the generations of a ship like this. The first generation are the volunteers, the chosen ones, the pioneers. They board with purpose, with conviction, with the knowledge that they are participating in the greatest adventure in human history. They accepted the trade. They gave up Earth, freely and willingly, for the chance to send humanity to the stars. Their motivation is internally generated and deeply felt. They will experience grief for Earth, for the friends and family they left behind, for the open sky and the feel of rain. But their grief is tempered by purpose. Even so, depression and regret will affect some. The overview effect, the profound cognitive shift reported by astronauts who see Earth from space, is awe-inspiring when you know you are coming back. When you watch Earth shrink into a pale blue dot and know you will never return, it becomes something else entirely. It becomes loss. Absolute, irreversible loss. The second generation is born on the ship. They never chose this life, but they are raised by people who did. Their parents can tell them stories of Earth, of beaches and mountains and thunderstorms and autumn leaves, of cities and countryside, of wild animals and open horizons. This generation has inherited cultural memory of Earth, even though they have never experienced it. They can understand what was sacrificed and why. They have a relationship, however abstract, with the mission's purpose. The third generation is different. No one alive on the ship has ever seen Earth. Earth is not a memory now. It is a story, a myth. Almost, the grandparents who saw it are dead or very old. The mission was chosen by people who are gone. The destination, a star that is no closer in any perceptible way, means nothing emotionally. It is just a name, a concept, an abstraction. This is the generation where the question begins to form. Why are we doing this? Why should I spend my life maintaining this ship for people who will not exist for 100 years? What is in this for me? By the fourth and fifth generations, the disconnection is complete. Earth is ancient history. The mission is an inherited obligation, not a choice. The ship is not a vehicle. It is just the world. The only world they have ever known or will ever know. Some will maintain faith in the mission out of duty or tradition. Others will not. And those who do not, what do? They have nowhere else to go. They are trapped in a life sentence they did not earn, serving a purpose they do not feel, for beneficiaries they will never meet. This is not speculation. This is what we know about human psychology applied to an unprecedented situation. Humans need purpose. Humans need autonomy. Humans need novelty. Humans need connection to something larger than their immediate environment. On a generation ship, all of these are compromised. Novelty is perhaps the most underestimated need. The human brain is wired to seek new experiences. Our dopamine systems, our reward circuits, our motivation pathways all depend on novelty. The same corridors, the same rooms, the same faces, the same recycled air with the same chemical tang, the same hydroponic farms growing the same crops in the same configurations, day after day, year after year, decade after decade. The brain habituates, the world becomes grey. Anhedonia, the inability to feel pleasure, creeps in. Depression follows. Not for everyone, but for enough people to create a critical mass of non-functional crew members. And there is the claustrophobia. Not in the clinical sense necessarily, though that too, but in the existential sense. The knowledge that beyond these walls is nothing, that you cannot walk to a horizon, cannot drive to a new city, cannot travel to a different country, cannot even go outside for your entire life. Research on long-term prisoners shows that even large prison facilities cause psychological damage through the simple mechanism of denied freedom of movement. And prisoners know there is a world outside. They know they might one day be released. Generation ship inhabitants have neither of these comforts. The psychological toll would manifest in predictable ways. Increased rates of depression and anxiety disorders. Substance abuse, if any intoxicants are available or can be manufactured. Increased aggression and interpersonal violence. Self-harm and suicide. Apathy toward maintenance duties. Social withdrawal. And these are not individual problems, they are societal problems. Because a ship where a significant percentage of the population is psychologically unwell is a ship where critical maintenance is not being performed, where social cohesion is breaking down, and where the complex cooperative behaviors needed to keep the ship running are failing. Intergenerational trauma is another factor. If the first generation experiences the grief of leaving Earth, and if subsequent generations experience the ongoing stress of confinement, each generation passes trauma to the next. Research on adverse childhood experiences shows that children raised by traumatized parents are more likely to develop psychological problems themselves, even without experiencing the original trauma directly. After several generations of accumulated intergenerational trauma, the baseline psychological state of the population would be significantly impaired compared to the original crew. And we have not even discussed the interpersonal dynamics of permanent confinement. People in isolated groups inevitably develop conflicts. On Earth, when relationships break down, you can leave. You can move to a different city. You can change jobs. You can make new friends. On a generation ship, you cannot escape anyone. Your worst enemy, the person you despise most in the world, will be in your sight for the rest of your life. And your children's lives. And their children's lives. Feuds would develop and persist across generations. Grudges would calcify into permanent social divisions. The ship would fracture into factions, clans, tribes, each occupying different sections, each jealously guarding their resources and territory. This brings us to the next great challenge, the societal challenge. Because even if individuals remain psychologically healthy, which they will not, the question remains whether 10,000 people can maintain a complex, technologically sophisticated, cooperative civilization in total isolation for 200 years. And history gives us a very clear answer. No, they cannot. And here is why. Luke Kemp, a researcher at the Center for the Study of Existential Risk at Cambridge University, published an analysis in 2019 examining the lifespan of civilizations throughout human history. His findings showed that the average lifespan of a civilization is approximately 340 years. Some last longer, many last far less. But the critical point is that no isolated civilization has ever maintained itself indefinitely. They all eventually collapse, and isolation accelerates the process. A generation ship is not merely isolated. It is the most extremely isolated human community that has ever existed, totally cut off from all external trade, all external cultural exchange, all external genetic exchange, all external resources, and all external governance checks. Every single historical factor that contributes to civilizational collapse is amplified on a generation ship. Let us walk through the mechanisms. Governance: who rules the ship? This is not an abstract political science question. It is a survival question. The ship requires complex maintenance, resource allocation, population management, conflict resolution, and long-term planning that spans generations. Someone must make decisions. Someone must enforce those decisions. But who, and how are they chosen? And what prevents them from abusing their power? Democracy requires an educated, informed populace capable of evaluating complex technical decisions. It requires free flow of information, fair elections, and the ability to hold leaders accountable. These things are difficult to maintain even in large, resource-rich societies with long democratic traditions. In a small, confined, resource-limited community under constant existential stress, the pressures toward authoritarianism are enormous.